We have another example on the board. We have to find Z total. Please notice that we have given Y total. So if you have given Y total, we can find the conductance and we can find the angle. Okay, so what I'm going to do right now, I'm going to simply find the conductance. I have G is equal 1 over R, which is equal 1 over 8 coulombs, which is equal 125 microsiemens. Okay. Also, I'm going to find right away the capacitive susceptance. BC is equal 1 over Z sub C, which is equal 1 divided by 12 coulombs and angle of negative 90 degrees. So I'm going to get 83.33 microsiemens and angle of 90 degrees. Next, we are going to find the angle. Before I'm going to do calculations in order to find angle, I'm going to draw the admittance diagram. First, you're supposed to draw the complex plane. Okay, I have real axis, I have imaginary axis, and I have conductance. This is my G, and this is going to be my capacitive susceptance, BC. Please notice that capacitive susceptance has angle 90 degrees. And I will talk also about the inductive susceptance, which is greater than BC. So this is my BL. So if you are going to add these two phasors together, you are going to get the negative angle. Okay, you are going to end up with the angle of negative 90 degrees. Why? Because you have BC less than BL. So your angle is going to be in the fourth quadrant of the complex plane. So means we are going to talk about the negative angle. Okay, so if you are going to add this one to this one, so you are going to have approximately value of your B total, somewhere like this. And if you are going to draw the total admittance, you are going to have negative angle. So it means that anytime BL is greater than BC, right, your angle next to Y total is going to be negative. The angle next to Z total is going to be positive. Why? I'm going to explain this later on. So what we're supposed to do next? We're supposed to write the formula. Okay, this is my Y total, of course. So I have angle theta is equal inverse cosine, and this is going to be nothing else, just G over Y total. So I have inverse cosine, and we found G is equal 125 microsiemens over Y total, which is given 210 microsiemens. And if you are going to perform the calculations, you're supposed to obtain the angle negative 53.47 degrees. Okay, again, we have negative sign because BL is greater than BC. Okay, I explained everything on this diagram. So this is my angle next to Y total because we spoke about the admittance diagram. Now we can write that I have Y total equals 210 microsiemens and angle of negative 53.47 degrees. Okay, so this is my Y total. And this angle, I used to mark theta Y. It means that this angle, I mean, in this case, negative 53.47, is going to appear next to the value of Y total. Because later on, I'm going to look for the total reactive power. I'm going to convert my total admittance to the rectangular form, okay? So this is going to be equal 125 microsiemens minus J 168.74 microsiemens, where the real part is my conductance and imaginary part is my inductive susceptance, but it's inductive because I have negative sign, but we're supposed to call this at this moment be total, okay? This is the combination of the capacitive susceptance and inductive susceptance. So this is B total over here, okay? Of course, this is inductive susceptance because I have negative sign, but this is at this moment the combination. Okay, this is my BT. So what I'm supposed to do next, the problem is asking me for Z total. So Z total is equal 1 over Y total. So this is equal 1 divided by 210 microsiemens, an angle of negative 53.47 degrees. This is equal 4.76 kiloohms, an angle of 53.47 degrees. So this is my Z total. Please notice that we found Z total. Now we are going to find IL. In order to find IL, we're supposed to find the inductive susceptance. In order to do so, I'm going to use the formula which says B total is equal BC plus BL. In order to find BL, I'm going to solve this formula for BL. So if BL is equal BT minus BC, where B total we've found is equal 168.74 microsiemens, an angle of negative 90 degrees, because negative J is my negative 90 degrees, minus BC, which is equal 83.33 microsiemens, an angle of 90 degrees. Okay, so BL is equal 252.07 microsiemens, an angle of negative 90 degrees. Okay, so this is BL. Now, in order to find the current which goes through the inductor, I'm going to find voltage source, because I'm going to use Ohm's law. So voltage source is equal I total times Z total, because I want to keep voltage source having angle of 0 degrees. I'm not going to include any angles to my calculation. So I have I total is given 20 milliamps times Z total, which is over here, 4.76 kilohms, 4.76 kilohms, and everything is equal 95.2 volts. Okay, so this is my voltage source. So next you're supposed to write the Ohm's law. So IL is equal voltage source times BL, where voltage source is equal 95.2 volts times BL 252.07 microsiemens angle negative 90 degrees. So IL is equal 24 milliamps and angle of negative 90 degrees. So this is my current IL. Next we are going to find the true power. True power is equal voltage source raised to the second power over the resistance. Please notice that we are talking about the parallel circuit, so voltage source is equal VR, this is also equal VL, and this is also equal VC. So if I'm going to write in my formula VR or VL or VC or voltage source, it doesn't make any difference. Okay, so true power in this case is equal voltage source square over R, which is equal, we found that the voltage source is equal 95.2 volts raised to the second power over the resistance, and resistance is equal 8 kiloohms. So the true power is equal 1.13 watts. Next we are going to find the total reactive power. The formula says Q is equal voltage source raised to the second power times B total. Okay, so this is equal 95.2 volts raised to the second power times BT, and we found that BT is equal 168.74 microsiemens. So Q is equal 1.52 volt ampere reactive. So this is my total reactive power. Next we're supposed to find the apparent power. S is equal voltage source raised to the second power over Z total. Voltage source we found is equal 95.2 volts raised to the second power over Z total, which is equal 4.76 kiloohms. This is equal 1.9 volt amp. Okay, so this is my apparent power. Next, we are going to find the power factor. Power factor is equal cosine of angle theta. Okay, angle theta is the angle which is next to Z total. So I have cosine of angle 53.47 degrees. Okay, so this is equal 0.595 lag. Okay, because the current, the total current is going to lag the voltage source by angle of 53.47 degrees. Okay, let me explain you this one more time. I total is equal voltage source, and we said voltage source has angle of 0 degrees over Z total and angle of 53.47 degrees. Okay, so this is the angle which is next to Z total. So if you are going to divide the magnitudes, you're supposed to obtain 20 milliamps, and you're supposed to subtract the angles. So 0 minus 53.47 degrees is negative 53.47 degrees. So basically it means that my current, I total, is going to lag my voltage source by 53.47 degrees. That's why I'm supposed to write a word lag next to the value of power factor. Okay, so this is why we have lag up there. Next, we're supposed to find the voltage across resistor and the reactive component in the series equivalent circuit. In order to do so, we're supposed to write again that Z total is equal 4.76 kilo ohms and angle of 53.47 degrees, and convert this to rectangular form. Okay, so we will obtain 2.83 kilo ohms plus J 3.82 kilo ohms. Okay, where my real part of my answer is my resistance in the series equivalent circuit, and this is my reactive component. Okay, so this is my X of S, which is nothing else, just in this case, because I have positive sign, this is X of L S. So what we can do right now, we can basically draw the series equivalent circuit. So I have angle theta, I have resistor, and I have inductor. Okay, so this is my RS equals 2.83 kilo ohms and X of L equals 3.82 kilo ohms, and this is my voltage source, which is equal 95.2 volts. Okay, so next I'm supposed to find voltage across resistor and across the capacitor. You have to realize that the total current which will flow in this circuit is equal to the total current which will flow in this circuit. Okay, these two values are identical. That's why I can use Ohm's law and simply write that V R S means voltage across the resistor in the series circuit is equal I total times RS, where I total is equal 20 milliamps and angle of negative 53.47 degrees times RS, which is equal 2.83 kilo ohms. Everything is equal 56.6 volts and angle of negative 53.47 degrees. Okay, so this is the voltage across resistor in my series equivalent circuit. Next, I have to find the voltage across the inductor, VLS, which is equal I total times XLS, which is equal 20 milliamps and angle of negative 53.47 degrees times X of LS. So I have 3.82 coulombs and angle of 90 degrees. So this is equal 76.4 volts and angle of 36.53 degrees. Okay, so this is my voltage across the inductor. Next, we are going to verify if our answers are correct. We are going to use Kirchhoff voltage law, which says that if I'm going to add these two voltages, right, I'm going to obtain the voltage source. So I have voltage source is equal the sum of the voltage drops across all components. I have just two components, so VRS plus VLS. So this is equal 56.6 volts and angle of negative 53.47 degrees plus 76.4 volts and angle of 36.53 degrees. This is equal 95.08 and angle of negative 0.002 degrees. So we can say that this is very close to the voltage source, which we found that is equal 95.2 volts. So it means that our calculations up to this moment are okay. In order to find the true power in the series equivalent circuit, I'm going to use the formula P is equal I total square times RS, where I total is equal 20 milliamps raised to the second power times RS 2.83 coulombs. This is equal 1.13 watts. Let me remind you that the power which we obtain in the parallel circuit, I mean the true power, was exactly the same. It was 1.13 watts. So it means that we are doing everything fine. Next, we are going to find the total reactive power in the series equivalent circuit. Of course, this was the true power in the series equivalent circuit. So this is nothing else, just I total raised to the second power times the total reactance, right, in the series equivalent circuit, which is simply nothing else, just X of LS. This is X of LS. Save X of LS. So this is equal 20 milliamps raised to the second power times X of LS, so which is equal 3.82 coulombs. 3.82 coulombs. Everything is equal 1.52 volt ampere reactive. Okay, if you are going to compare this answer with the total reactive power in the parallel circuit, you will see that we get exactly the same value. So it means that the problem is solved correctly.